know and love circuits, but how exactly do they work? To understand this complex question, we must first begin by understanding the behavior of single-charged particles.
Let's say we have two positive charges and place them next to each other. Ever heard of the saying opposites attract? Well, this applies not only to love but to charges as well. These like charges will immediately repel even without contact. But if they're not touching, then what moves these particles? We can visualize this invisible force as lines of force called electric field lines.
Each charged particle produces its own electric field. A positively charged particle's electric field points outward, whereas a negatively charged particle's electric field points towards the particle.
This means that if we have a neutrally charged particle and place it close to the positively charged particle, it'll be pushed away. And if we put the neutrally charged particle close to a negative particle, it will be pushed towards the negative charge. Let's say that we now have a small positive charge and a larger positive charge. If we're a distance r from both particles, we'd find that the electric field E produced by the greater positive charge is much stronger. So, we can say as the magnitude of the charge, or Q, increases, the strength of the electric field produced by that charge also increases. Now, let's instead imagine we have two positive charges of the same magnitude or size, but we are different distances away from them. We would find that as we move farther away from the point charge, the electric field strength decreases. So, in this case, the electric field a distance r1 away is greater than the electric field distance r2 away. Based on these observations, we can find that E is equal to Q, which is charge strength, over r squared, where r represents distance, times a constant. Now let's say we have two plates of charge, one positive and one negative. Given that the charges are equal strength, the electric field between these plates would look something like this, using the relationship for E we previously established. If we placed a small positive charge at A and release it, the electric field will push it towards point B. At point P, the particle would have a high speed and a high kinetic energy, which means energy for movement. But since this energy must come from somewhere and the particle was initially at rest, the particle must have been initially storing some energy. We call this energy electric potential energy. Let's say we have a small positive chest charge but started at point B. The charge is happy here, so if we want to move it back to point A, we must do some kind of work on the particle. If we divide this quantity by the magnitude of the charge, we can call this potential difference or voltage. If you take an object with a potential difference, such as a battery, and attach a wire to it, this will cause electrons to flow, lighting up this bulb and powering the world's technology.